Black holes are among the most mysterious objects in the universe. Detecting them directly is extremely difficult, since they emit no light and are therefore almost invisible to observers. However, their presence can be inferred through indirect effects. One of the most important is the bending of light. If a black hole lies between Earth and a distant galaxy, its powerful gravitational field deflects the light coming from that galaxy. This phenomenon is known as gravitational lensing. It occurs not only near black holes, but also when light passes through massive structures, such as galaxies and clusters of galaxies. Yet the capabilities of black holes do not end there. In recent years, science has uncovered an entire range of astonishing properties of these objects. It has turned out that black holes can move at near light speeds, behave extremely aggressively, and display far more complex and flexible behavior than previously expected. Below, we will discuss 10 superpowers of black holes known to modern science. The first can be called the cosmic vortex. As the name suggests, black holes are capable of rotating at incredible speeds. The spin rate of supermassive black holes can reach about 84% of the speed of light. One example is the black hole in the galaxy NGC 1365, located roughly 60 million light-years from Earth. Its diameter is about 3.2 million kilometers, and its mass is several million times that of the Sun. As it rotates, it warps not only space but time itself, creating a blazing whirlpool of X-ray radiation, gas, and dust falling into its depths. Most likely, matter flows into the black hole predominantly from one direction, which gives rise to such an extreme rotation rate. The second superpower is sociability. Black holes often form groups, and observations suggest this happens far more frequently than previously believed. Many large galaxies are literally seeded with supermassive black holes. Their immense sizes raise doubts that they could have formed from single stars. For a long time, scientists believed that supermassive black holes originated in dense star clusters, either from dying binary stars or through the gradual merger of smaller black holes that eventually grow into true cosmic giants. The third ability is the fiery Rasengan. Black holes can eject clumps of matter the size of planets, as if playing cosmic snowballs. In some cases, these outbursts may even be directed toward our galaxy. Theoretical calculations and computer simulations suggest that near the Milky Way's central black hole, Sagittarius A, there may be a massive star that passes dangerously close, roughly once every 10,000 years. During such encounters, the black hole strips material from the star, forming a long stream of superheated matter. Part of this material is swallowed by the black hole, while the rest is expelled into space. Some of the matter remains relatively nearby and can merge into dense clumps the size of planets. In certain cases, these clumps can grow as large as Neptune or even Jupiter and be hurled into intergalactic space at speeds of up to 2.2 million kilometers per hour. According to researchers, tidal disruption events may eject around 100 million such objects into the cosmos. The fourth superpower is the ability to hide a galaxy's past. The ALMA radio telescope array has made it possible to study in detail the so-called Taurus A ring of gas and dust surrounding a black hole shaped like a donut. The object studied lies about 47 million light-years away in the constellation Cetus. Thanks to ALMA's remarkable sensitivity, scientists were able to measure the torus's width, which is approximately 20 light-years. By studying these structures, astronomers can uncover valuable clues about a galaxy's history. For example, an asymmetric torus may indicate that the galaxy underwent a merger in the past. The fifth superpower is consuming matter at extraordinary speeds. Black holes are inherently insatiable. Billions of light-years away in the direction of the constellation Coma Berenices lies an exceptionally bright galaxy known as PJ211. Its brightness is due to a central black hole that absorbs matter at speeds of up to 100,000 kilometers per second. Researchers have found that the galaxy's X-ray emission shows a strong redshift, which may indicate that matter is plunging directly toward the center of the supermassive black hole at speeds reaching about 30% of the speed of light. In this case, the gas barely orbits the black hole and instead falls inward along an almost straight path. We now move on to the sixth superpower, known as the lone wanderer. A black hole can behave like a true interstellar lone wolf, roaming through space. For a long time, scientists suspected that black holes could be ejected from their host galaxies under certain conditions. Strong evidence for this hypothesis comes from quasar 3C 186, located about 8 billion light-years away and possessing a mass of roughly 1 billion suns. Observations show that this quasar is rapidly leaving its native galactic cluster. Calculations indicate that the gas cloud associated with it is moving away at about 7.6 million kilometers per hour. At such a speed, the distance from Earth to the Moon could be covered in just 3 minutes. Astronomers believe this dramatic escape was caused by a gravitational wave recoil produced during the merger of two supermassive black holes. The resulting impact was comparable in energy to the simultaneous explosion of hundreds of millions of supernovae, literally kicking the quasar out of its original position. The seventh superpower is theft. Surprisingly, smaller black holes can steal material from much larger ones. To date, 5 black hole mergers accompanied by detectable gravitational waves have been officially confirmed. One of these events stood out in particular. Initial estimates suggested the merging black holes should each have had masses between 10 and 15 solar masses, but observations revealed that both exceeded 20 solar masses. After analyzing the data, scientists concluded that these black holes had gained mass by siphoning material from a nearby supermassive black hole at the center of their galaxy. Before becoming black holes, they were massive stars that collapsed during stellar evolution and gradually drifted toward the galactic center, where a supermassive black hole was actively consuming gas and dust. These two lightweights managed to steal part of that material, nearly tripling their mass before eventually merging with each other. The eighth superpower is called extra rations. Black holes can use magnetic fields as a feeding mechanism. One of the key factors influencing a black hole's growth is the strength of its magnetic field. While studying the galaxy Cygnus A, located about 600 million light-years from Earth, scientists discovered an exceptionally powerful magnetic field at its center. Further analysis showed that the central black hole of Cygnus A is extremely active and is considered the most powerful extragalactic radio source in its constellation. This radiation is produced as the black hole consumes surrounding matter, with the magnetic field playing a crucial role by channeling material directly into the black hole's depths. The presence or absence of a strong magnetic field largely explains the difference between active galaxies like Cygnus A and relatively quiet ones such as our Milky Way. The ninth superpower is stealth. In this respect, black holes are unrivaled. They can hide even within tiny galaxies. A striking example is the galaxy Fornax A in the constellation Fornax. It contains about 100 million stars, a negligible number compared to the Milky Way's hundreds of billions. The galaxy's radius is only about 300 light-years. Despite its small size, it is one of the densest galaxies known. The discovery of a supermassive black hole within it marked only the fourth known case of such an object being found inside an ultra-compact galaxy. Astronomers estimate that this black hole accounts for roughly 4% of the galaxy's total mass, whereas in most other galaxies the figure is closer to just 0.3%. And finally, the 10th superpower, the crushing blow. A black hole is capable of consuming an object the size of our Sun in just 2 days. Not long ago, astronomers discovered an extraordinarily voracious quasar that formed about 12 billion years ago. Its central black hole devours the equivalent of one solar mass every 48 hours. With such an appetite, it grows at an astonishing rate, and its radiation outshines an entire galaxy by thousands of times. This glow is produced by the intense heating of gas and matter as they fall into the black hole. How this object managed to gain so much mass so quickly in the early universe remains a mystery, but its destructive potential is undeniable. If such a monster were located at the center of the Milky Way, it would shine 10 times brighter than the full moon in the night sky, outshining most stars and wiping out all life with its lethal X-ray radiation. Black holes are truly dangerous entities. But what do you think? Do they still hide other unknown superpowers? Each of us has wondered at least once just how vast our universe truly is. Its age and scale lie far beyond the limits of human imagination. Somewhere within this boundless expanse drifts our tiny planetary home, Earth, inhabited by humanity. Despite our modest place in the cosmos, over recent decades, we have developed many intriguing and thought-provoking theories about the origin and structure of the universe. Today, the Big Bang theory is nearly as universally accepted as the fact that Earth orbits the Sun. According to this model, about 14 billion years ago, spontaneous quantum fluctuations in absolute nothingness gave rise to the universe. An entity comparable in size to an elementary particle expanded within fractions of a second to unimaginable proportions. Yet even this theory leaves many unanswered questions, which is why scientists, physicists, and even science fiction thinkers continue to propose alternative ideas. One such idea is the steady-state theory. Its proponents, particularly influential in the 1950s and 1960s, argued that the universe has always existed in an unchanging state. While they did not deny cosmic expansion, they believed it was balanced by the continuous creation of new matter from nothing. Another concept is the cyclic model. Rather than rejecting the Big Bang, it proposes that many Big Bangs have occurred. In this view, the universe repeatedly expands to a maximum size, then contracts and undergoes a new bounce. Our universe, therefore, would be just one link in an endless chain of births and destructions. There are also string theory and M theory, each with many variations. In general terms, they allow for the universe to continuously reproduce itself. Some scientists suggest that our universe arose from quantum fluctuations in a previous one, implying that similar processes could someday generate new universes. In the boldest interpretations, even the smallest event, a simple choice, could give rise to an alternate reality with a different outcome. An even more exotic idea is the holographic theory. According to this hypothesis, our entire reality may be a kind of hologram created by the universe itself. In this case, the night sky would merely be a surface onto which all galaxies and stars are projected. But which of these theories is closest to the truth? To explore this, we must travel about 500 years into the past, to the Renaissance, when Nicholas Copernicus rejected the idea that Earth sits at the center of the cosmos. His insight became one of the greatest scientific breakthroughs in history and laid the foundation for our understanding of cosmic structure and physical reality. Today we know that Earth orbits an ordinary middle-aged star, the Sun, which is just one of roughly 200 billion stars in the Milky Way galaxy. Our galaxy, in turn, is only one of what may be hundreds of billions of similar structures in the observable universe. By human standards, the universe contains an unimaginable amount of matter and an even more staggering volume of space. Imagine that you are located in a distant galaxy and wish to describe the route to Earth. First comes the third planet from the Sun, then the solar system itself, situated in the Orion Arm on the outskirts of the Milky Way. Next is the Milky Way as part of the local group of galaxies, which includes more than 50 members and spans about 7 million light-years. This group lies on the edge of the Virgo cluster, which contains over 1,000 galaxies and is located roughly 50 million light-years away. The Virgo cluster, in turn, is part of a local supercluster that unites hundreds of galaxy clusters across scales of about 100 million light-years. Superclusters are among the largest structures in the universe. They include both galaxy groups like our local group and enormous clusters containing hundreds of galaxies. All of these structures are gravitationally connected, and their precise boundaries are extremely difficult to define. Meanwhile, the universe continues to expand, with galaxies drifting apart like points on the surface of an inflating balloon. The scale of these motions is so vast that astronomers created a catalogue of cosmic flows, initially mapping the movement of 1,800 galaxies within 130 million light-years of the Milky Way, and later expanding the dataset to nearly 8,000 galaxies within a radius of 250 million light-years. Analysis of this data unexpectedly revealed a previously unseen structure, a gigantic region in which galaxies flow toward a single gravitational center, much like streams of water converging into a valley. This immense system was named Laniakea, meaning immeasurable heavens in Hawaiian, in honor of ancient Polynesian navigators who crossed the Pacific by reading the stars. Laniakea is not merely another line in our cosmic address. It spans about 500 million light-years in diameter and contains roughly 100,000 galaxies, with a total mass of around 100 quadrillion solar masses. It includes both the Virgo cluster and the Great Attractor, a region of especially strong gravitational pull. Within Laniakea, The motion of galaxies resembles water flowing downhill toward a gravitational basin. By studying the structure and dynamics of this colossal system, scientists gain vital insights into the past and future of the universe. Mapping galaxies and analyzing their motion helps us better understand how galaxies form, grow, and migrate through cosmic space. Future research may also reveal new details about dark matter, an invisible substance that makes up about 80% of all matter in the universe. On cosmic scales, everything is relative. A world that seems unimaginably vast to us is, in reality, just a small part of a much larger structure, the solar system. And the solar system itself is little more than a grain of sand against the backdrop of the Milky Way. To visualize this, imagine dumping a truckload of sand over a football field and then picking up a single grain. That grain represents the solar system compared to the galaxy. Humanity continues to make new scientific discoveries. Each breakthrough feels like a moment of revelation, a shock that overturns our established view of reality. This happened when we learned that Earth is spherical, that it orbits the Sun rather than the other way around, and that countless other galaxies exist beyond our own. This process never stops. With every new answer, new questions arise, including the ultimate question of how the universe itself began. Have you found your own answer? Have you ever wondered what will happen when nothing remains? Or, in other words, what infinity truly means? You have probably heard of the infinite monkey theorem. Even if the name is unfamiliar, the idea is well known. If a monkey types on a keyboard for an infinite amount of time, it will eventually produce any given text, even all volumes of War and Peace. But what does an indefinite amount of time really mean? In essence, it means infinity. Try to imagine time without an end, billions, trillions, and trillions upon trillions of years. Now let us return to the central question. What happens when matter and gravitational interactions are torn apart in an endlessly expanding universe? What occurs during the so-called Big Rip, when even the concept of time becomes conditional? If the hypothesis of dark matter is correct, the universe may eventually disintegrate into the smallest elementary particles, quarks uniformly distributed throughout space. Their entropy, that is, the measure of disorder in the system, would reach its maximum possible value. The Austrian physicist Ludwig Boltzmann, the founder of statistical mechanics, proposed that even at maximum entropy, the spontaneous emergence of locally ordered structures within a closed system cannot be ruled out. In fact, if we think about it, our orderly world with relatively low entropy is merely a rare deviation from the universe's dominant state of chaos. To visualize this, let us conduct a thought experiment. Imagine the universe as an isolated sphere uniformly filled with air molecules, which play the role of elementary particles. These molecules move randomly within the sphere. If one were to observe this system for an infinite amount of time, every molecule would eventually occupy every possible position more than once. As a result of this random exploration of states, localized regions of lower entropy would inevitably appear. Areas of higher density or temporarily organized structures. Over time, the molecules would return to their original chaotic state. This process might take an unimaginably long time, but infinity is precisely the resource the universe would possess after the Big Rip. Now replace the air molecules with quarks in a far future universe. The universe itself becomes the monkey from the famous theorem, endowed with infinite time to cycle through all possible configurations of elementary particles. If an observer had enough patience, a random region of space might momentarily form an apple, a plant sprout, or even a mannequin in a spacesuit sitting behind a steering wheel. Moreover, as configurations continue to be explored, elementary particles could eventually compress into a single, extremely dense point in space. This would resemble nothing other than the Big Bang, the event that gave birth to our universe, but even that is not the limit. One rare yet possible instance of a local decrease in entropy could be the emergence of consciousness, a thinking entity capable of self-awareness. After all, a human being, along with their memories and identity, is merely a particular arrangement of elementary particles. Theoretically, such an entity need not resemble a human at all. It could be a higher-order intelligence, perhaps even capable of creating or simulating an entire universe within itself. How long would one have to wait for such an event? According to the work of the prominent theoretical physicist Andrei Dmitrievich Linde, it might occur roughly once every 1050 years. For comparison, the current estimated age of our universe is only about 13.8 billion years, utterly negligible next to that number. Given an eternity, the emergence of such a mind becomes inevitable. This hypothetical phenomenon is known as the Boltzmann brain. One might be tempted to treat this idea with irony, if not for the profound philosophical paradox it raises. If an infinite number of opportunities for spontaneous consciousness always outweighs the finite probability of consciousness arising through evolution, then why should we consider ourselves the original rather than one of countless random copies? This dilemma is known as the Boltzmann brain paradox. As Andrei Linde put it, the logic of quantum field theory and inflationary cosmology forces me to admit that in the infinitely distant future, new and new copies of my consciousness will arise in the vacuum. But if that is the case, why should I believe that my current self is the original rather than one of those copies? To conclude on a philosophical note, one might recommend Martin Heidegger's book, Nietzsche's Metaphysical Concept and its Role in European Thought, which explores the idea of eternal recurrence. In it, Friedrich Nietzsche's revolutionary notion is examined, the idea that life, with all its joys, suffering, thoughts, and fleeting moments, must repeat itself endlessly in exactly the same sequence. This life as you now live it and have lived it, you will have to live once more and innumerable times more. Doesn't this idea seem strikingly aligned with modern conceptions of the universe? We still know remarkably little about the cosmos, as it hides countless unexplored phenomena. One such class of objects is dwarf galaxies. What makes them special, and how do they differ from others? Let us explore this question using the unusual galaxy DDO 68 as an example. A dwarf galaxy, as the name suggests, is a relatively small stellar system containing only a few billion stars, negligible compared to the Milky Way's roughly 300 billion. Galaxies are classified as dwarf if their luminosity is about 100 times lower than that of the Milky Way. The first dwarf galaxies were discovered in the late 1930s. Astronomers initially identified an unknown star cluster in the constellation Sculptor containing about 10,000 stars. Soon after, a similar object was found in the constellation Fornax. When telescopes at the Mount Wilson Observatory were used to study these systems, astronomers detected Cepheid variable stars, pulsating stars that allow accurate distance measurements. This revealed that the objects lay beyond the boundaries of our galaxy, leading to the discovery of a new type of galaxy with low surface brightness. The large-scale discovery of dwarf galaxies began in the 1950s with the Palomar Sky Survey, conducted using a 120-centimeter Schmidt camera at Mount Palomar Observatory. It became clear that dwarf galaxies are the most common type of galaxy in the universe. Their stellar ages, shapes, sizes, and nebular content reveal unique characteristics. Though studying them is far from simple, we live in an age of overwhelming information, much of which passes unnoticed. Over time, astronomers succeeded in observing how dwarf galaxies group together before merging into larger systems. Compact, gravitationally bound groups of dwarf galaxies were identified for the first time. Using data from multiple telescopes, researchers discovered 7 such groups, each containing 3 to 5 dwarf galaxies, located between 200 and 700 million light-years from Earth. The mass of ordinary matter in each group ranged from 4 to 20 billion solar masses. However, their motions and gravitational influence clearly indicated that dark matter vastly outweighs visible matter in these systems. These observations are critically important because modern cosmological models suggest that nearly all large galaxies, including the Milky Way, formed through the merger of smaller dwarf galaxies. Detecting such mergers is extremely difficult, since most occurred billions of years ago during the formation of our galaxy. Moreover, dwarf galaxies are faint and distant, easily overshadowed by massive galaxies into which they have already been absorbed. Today, dwarf galaxies are most often observed as satellites of larger systems. Nevertheless, the search continues, and with impressive results. In addition to the Hubble Space Telescope, astronomers employed the Galaxy Space Observatory, capable of detecting radiation in both visible and ultraviolet wavelengths. This allowed researchers to capture extraordinarily detailed images of distant regions of the universe. Over the course of a year, scientists studied nearby galaxies, analyzing star clusters, spiral arms, and even individual stars. The result was the most detailed catalogue of cosmic light sources ever assembled in the history of astronomy. By combining new observations with archival data, researchers analyzed about 50 galaxies and produced a highly detailed map of the stellar sky. The ultraviolet range played a crucial role in this work, as it is the primary indicator of the youngest and hottest stars. By studying ultraviolet radiation, astronomers can determine stellar ages and reconstruct the history of star formation. Special attention was given to dwarf galaxies, where active star formation is still taking place despite their small size. The final catalogue included more than 30 million stars, each at least 5 times more massive than the Sun. Their ages range from 1 million to several billion years, with the youngest stars standing out most clearly in ultraviolet light. It was during these studies that the unusual dwarf galaxy DDO 68 was discovered. It is located about 40 million light-years from Earth in the constellation Leo. Its total mass is approximately 100 million solar masses, only 1,000th of the mass of the Milky Way. This tiny galaxy is notable for its extremely low abundance of heavy chemical elements, a characteristic typical of very young galaxies where star formation has only recently begun. Previously, it was believed that stars in DDO 68 began forming about 100 million years ago, which is very recent by galactic standards. However, more detailed studies revealed the presence of much older stars as well, at least 1 billion years old. This finding contradicts the galaxy's low metallicity. Since the longer star formation continues in a galaxy, the more heavy elements should accumulate. These elements are produced in stellar interiors and dispersed into space during supernova explosions. One possible explanation is that heavy elements are being blown out of the galaxy by galactic winds. In addition, astronomers were intrigued by an elongated tail extending from DDO 68 and containing both stars and gas. This structure may have formed as a result of tidal effects caused by gravitational interactions with other galaxies. Observations using the Large Binocular Telescope revealed several tiny, extremely faint satellite objects near DDO 68, also composed of gas and stars. This discovery is particularly surprising because DDO 68 is considered an isolated galaxy. It does not belong to a large cluster and lies within what is known as a cosmic void. Moreover, the presence of satellites is generally uncharacteristic of dwarf galaxies. It is likely that interactions with these miniature companions led to the formation of the tail. The mass of each satellite is estimated to be about 100,000 solar masses, comparable to the faintest known satellites of the Milky Way. Such low-mass, low-luminosity galaxies are considered the closest modern analogues of the very first galaxies that formed in the universe. In ancient times, people believed they lived on a vast flat surface, dotted here and there with mountains and valleys. This view persisted for thousands of years until Aristotle, in the 4th century BCE, noticed that a ship sailing away into the sea does not disappear all at once. First, the hull vanishes, then the sails, and only afterward the mast. From this observation, he concluded that Earth must be spherical. But what can we say about the shape of the universe? Does it even make sense to ask this question? Can we determine the shape of the universe in the same way we determined the shape of Earth? Would we see infinite darkness, countless bubbles, a snow globe, or perhaps some kind of cosmic labyrinth? Determining the shape of the universe has proven to be far more difficult than originally expected. On one hand, it may be infinite. On the other, it could possess a complex yet finite geometry. Any reasoning about its shape must rely strictly on real astronomical observations. Otherwise, even the most elegant hypotheses are doomed to fail. Observations show that from any point in the universe, one can conceptually draw a sphere of arbitrary size within which the space of the universe exists. This suggests that cosmic space is a three-dimensional manifold. This immediately raises a question. What kind of manifold is the universe, and what is its true shape? According to theoretical calculations, there are so many possible options that a complete list does not yet exist. Nevertheless, science continues to make progress. Decades of astronomical observations have revealed key properties of the universe that significantly narrow down the range of possibilities. Among the most important are the topology of space and its curvature. It is crucial to understand that a finite universe does not imply the existence of a physical edge from which one could fall, like from an overcrowded spaceship. The surface of Earth provides a good analogy. It is finite, yet one cannot step beyond it by traveling along its surface. In the case of positive curvature, space resembles a four-dimensional sphere. Such a universe has a finite extent, but no boundary in the conventional sense. Two particles traveling in the same direction would eventually traverse the entire space and return to their starting point. This effect can be easily visualized using a balloon. A line drawn along its surface will eventually close in on itself. Such a model is possible if the universe contains enough energy to fully close space. In that case, cosmic expansion would eventually have to come to a halt. There is, however, another hypothesis: a universe shaped like a four-dimensional saddle. This corresponds to a space with negative curvature, lacking boundaries both in space and in time. If the energy density is insufficient, expansion in such a universe never stops. Two particles moving along parallel paths would drift farther and farther apart, never meeting, much like lines diverging on a saddle-shaped surface. A third possibility is a flat universe. In this case, the energy density is close to a critical value. Expansion may slow over time, but it does not necessarily stop. In such a geometry, particles move in parallel. They neither converge nor diverge. These three models, spherical, saddle-shaped, and flat, are relatively easy to imagine, but they do not exhaust all possibilities. More exotic options also exist. For example, a shape similar to a soccer ball resembles a spherical universe, while a donut-shaped torus can be mathematically flat, yet still finite due to the way space is connected. Some scientists suggest that large hot and cold spots observed in the universe may hint at such topologies. But let us return to the very beginning. If we accept the Big Bang theory, then at the moment of the universe's birth, there were no concepts of here and there, before and after. All matter was concentrated in a single point, with nearly zero size and almost infinite density. Time itself did not exist, nothing happened within that point, and outside it there was nothing at all. Then, for reasons still unknown, an explosion occurred, and the newborn universe began to expand rapidly. Matter and energy rushed outward in all directions at nearly the speed of light. Fundamental forces, nuclear, electromagnetic, and gravitational, emerged. From that moment on, time began to flow. Today, the age of the universe is estimated to be approximately 15 billion years. If this is the case, then the size of the observable universe can be roughly estimated by multiplying its age by the speed at which matter propagates. That is, the speed of light, about 300,000 kilometers per second. In reality, this speed may have changed slightly over time, but for the sake of simplicity, it can be treated as constant. The resulting number, although unimaginably large, is still finite. This means that the universe is vast, but not infinite, and therefore it must have some definite shape. The simplest and most intuitive assumption is a spherical shape. If matter expands outward from a single center at the same rate in all directions, a classical explosion would indeed produce a sphere. However, if the expansion rate is not uniform and space is not closed, the shape of the universe could be far more complex. For example, a flat or curved four-dimensional plane. In that case, the universe could be infinite. There is yet another intriguing idea. In the mid-20th century, Soviet physicist Dmitry Ivanenko proposed that the universe may be closed, while not obeying the laws of Euclidean geometry everywhere. This would mean that in certain regions, parallel lines could intersect or even merge into one another. In such a universe, a traveler moving straight ahead from a single point, say, from Earth, could eventually return to the starting location, although the journey would take an enormous amount of time. In this scenario, the universe might resemble a bottle, a gourd, or a bowling pin, something closed and highly non-intuitive. We have considered many possible shapes, yet none can be identified with certainty. Still, there is reason for optimism. Today, scientists are attempting to determine the geometry of the universe by studying relic radiation. The Big Bang released not only matter, but also electromagnetic radiation with unique physical properties. This relic radiation still fills all of space uniformly and can be distinguished from other cosmic signals. Modern techniques allow astronomers to measure the curvature of the observable universe, and as a result, its shape is gradually beginning to emerge. What we need now is simply more time and more data. So what do you think? What shape might the universe have? Share your thoughts. If you look up at the night sky from a location with good visibility, you will notice a dense, luminous band of the Milky Way stretching across the entire sky. While these stars and nebulae are breathtakingly beautiful, for astronomers they long posed a serious obstacle. The bright glow of our own galaxy makes it difficult to observe distant galaxies and large-scale structures hidden deep in space. These obscured regions became known as the zones of avoidance. As early as the late 1920s, Harlow Shapley and his colleagues began systematic studies of galaxies in the southern sky, using photographic plates taken with a 60-centimeter telescope in South Africa. By 1932, Shapley reported the discovery of 76,000 galaxies, brighter than 18th apparent magnitude, across an area covering roughly one-third of the southern hemisphere. In 1930, he published a note describing a distant cloud of galaxies in the constellation Centaurus, remarking that it was so extensive it might be one of the most densely populated regions known at the time. Official recognition came in 1989, when observations with a Schmidt telescope in the United Kingdom confirmed the existence of this structure, which was named the Shapley supercluster in honor of the astronomer who had made such significant contributions to its study. But what exactly is this supercluster, and why is it often referred to as a galactic archipelago? These questions have long fascinated astronomers, and for good reason. The Shapley supercluster is not merely another object in space, but a structure of truly exceptional scale and importance. One of the main challenges was reconciling two seemingly contradictory facts. On the one hand, matter in the early universe was distributed with remarkable uniformity, as evidenced by the extreme isotropy of the cosmic microwave background radiation reaching Earth. On the other hand, the present-day universe is highly uneven. Matter is concentrated into stars, galaxies, clusters, and superclusters, forming a complex hierarchy of gravitationally bound structures. To understand how such complexity emerged from an almost uniform initial state, scientists needed to identify the forces that played a decisive role in shaping the cosmos. We know that the Milky Way, like all galaxies, is in constant motion. There are no truly stationary objects in the universe. This led to the introduction of the concept of peculiar velocity, which describes motion relative to the cosmic microwave background. The local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller systems, moves at a speed of about 600 kilometers per second, relative to this background radiation. Further studies revealed that different structures move at different speeds. Dense clusters form in some regions, while enormous voids appear in others. This raised a new question. Which objects exert the dominant gravitational influence on the local group? Over recent decades, astronomers have calculated the contributions of all major sources of attraction, nearby galaxy clusters, superclusters, galactic walls, and cosmic voids. A major breakthrough came with the development of X-ray astronomy, which made it possible to peer beyond the zone of avoidance and identify the source of the strong gravitational pull. At first, it appeared to be an ordinary galaxy cluster, but it soon became clear that its mass was insufficient to account for the observed motion of the Milky Way. This realization only deepened the mystery. As technology advanced, astronomers eventually discovered that the true cosmic magnet is far larger than the Great Attractor. This object turned out to be the Shapley supercluster, one of the most massive structures known in the universe. Its mass is estimated at roughly 50 million billion solar masses. It lies about 650 million light-years from Earth, near the Vela supercluster, and has an elongated oval shape with an angular size several times greater than the apparent diameter of the Moon. Current estimates suggest that about 44% of the local group's motion is due to the influence of the Great Attractor. The remaining component arises from a global flow of matter in which a large region of the local universe, including the Great Attractor itself, is moving toward an even more powerful center of gravity located in the direction of the Shapley supercluster. The Shapley supercluster represents a region of exceptionally high galaxy density in the constellation Centaurus. Its mass is roughly 10,000 times greater than that of the Milky Way and about 4 times greater than the mass observed in the region of the Great Attractor. And yet, even this was not the end of the story. More detailed studies revealed that at the very center of this region lies an extraordinarily rich galaxy cluster known as Shapley 8. It should be noted that the region of the sky at a declination of around 30 degrees is extremely difficult to observe. As a result, data on distant galaxies in this direction accumulated very slowly. However, in recent years, thanks to observations made with several of the world's largest telescopes, astronomers have succeeded in measuring the positions and velocities of thousands of galaxies in this region. This has made it possible to study their spatial distribution and mutual motion. As a result, Shapley's original conclusion was confirmed. In the direction of the constellation Centaurus, near its boundary with Hydra, there truly exists a gigantic concentration of matter that includes numerous galaxy clusters and individual stellar systems. In the past, this structure was referred to by various names, the Centaurus supercluster or the Alpha region, but eventually the name Shapley supercluster became firmly established. Scientists then faced the challenge of determining the mass of this enormous supergalactic structure. At first glance, the task seems straightforward. Simply count the number of galaxies in the supercluster and multiply it by the mass of a typical galaxy. In practice, however, this approach fails. In addition to galaxies, the supercluster contains vast amounts of invisible intergalactic matter, whose total mass exceeds that of the matter concentrated within the galaxies themselves. Therefore, the total mass of the supercluster can only be inferred from the strength of its gravitational pull. But how can that be measured? According to Newton's second law, the force acting on an object is related to its acceleration. However, astronomers are currently able to measure galaxy velocities far more reliably than their accelerations. In some cases, velocity alone is sufficient. For example, knowing the orbital speed of a satellite around Earth and the radius of its orbit allows us to calculate Earth's mass. But this method works only when the object is moving along a stable, stationary orbit. If a star cluster is in a state of dynamical equilibrium, the velocities of its individual stars can indeed be used to determine its total mass. The same principle applies to galaxy clusters. However, this method cannot be applied to the Shapley supercluster because the largest structures in the universe have not yet reached a stationary state. This colossal but relatively diffuse region is still expanding, albeit much more slowly than in the past. The Shapley supercluster is so massive that its gravitational pull is extraordinary. It is capable of attracting not only thousands of galaxies, including our own, but even the Great Attractor itself. The scale of this phenomenon is difficult to comprehend. Inevitably, a question arises. If such a gigantic supercluster lies beyond the Great Attractor, what might exist even farther away? The deeper we penetrate into the mysteries of the universe, the more clearly we realize how little we truly know. There is a theory that the universe is infinite. However, the fact that we cannot see beyond the observable horizon does not in itself prove infinity. And if the universe is finite, then what lies beyond its boundaries? To begin addressing this question, we must understand what the cosmic horizon is, and how far into the universe we are actually able to see. It would be naive to assume that astronomers can observe arbitrarily distant objects simply by building larger telescopes. Such thinking ignores two fundamental limitations: the finite speed of light and the finite age of the universe. The speed of light, about 300,000 kilometers per second, is directly linked to how deeply we can peer into space. To look far into space is also to look far back in time. On a clear summer night, we can see the bright star Deneb in the constellation Cygnus. Despite being about 2,600 light-years away, it is easily visible to the naked eye. This means that the light we see today was emitted 2,600 years ago, during a time when entirely different civilizations existed on Earth. We observe the star not as it is now, but as it was millennia ago. It is even possible that it no longer exists today. Now consider the galaxy NGC 474, located roughly 100 million light-years away. The light we receive from it today began its journey when dinosaurs may still have roamed the Earth. By observing such objects, astronomers are literally looking into the distant past, which is why telescopes are often called time machines. This property of observation is enormously important, as it allows us to study the evolution of the universe. Want to see what the universe looked like 8 billion years ago? Simply point a telescope at galaxies whose light has taken 8 billion years to reach us through expanding space. However, this method has a fundamental limit. If the universe originated about 13.8 billion years ago, then that is the maximum amount of time light could have spent traveling. We physically cannot observe anything beyond that temporal boundary. Thus, despite its immense size, the universe is accessible to us only in part as a spherical region with a radius of about 13.8 billion light-years centered on the Milky Way. This region is known as the observable universe, and its boundary is called the cosmic horizon. It is important to understand that every point in the universe has its own cosmic horizon. Imagine a ship in the ocean. Each vessel has its own horizon beyond which the sailors cannot see. In the same way, every observer in the universe occupies the center of their own personal observable universe. This means that a hypothetical alien located exactly on our horizon would see around them ordinary mature galaxies and aging stars, much like those we observe nearby. At the same time, we would also lie on that alien's horizon. They would see our region of space as it was 13.8 billion years ago, long before the Milky Way, the Sun, or Earth existed. Gradually, we arrive at the concept of the afterglow of creation, a term proposed by British astronomer and writer Marcus Chown. It describes what an observer sees at the very edge of the universe, the faint remnant glow left behind by the Big Bang. During the first several 100,000 years after its birth, the universe was filled with hot, dense plasma through which light could not freely travel. When the universe reached an age of about 380,000 years, its temperature and density dropped enough for electrically neutral atoms to form. At that time, the entire universe was blindingly bright, comparable to the surface of the Sun. When we look toward the cosmic horizon, we do indeed see this primordial radiation. Over the past 13.8 billion years, it has traveled through an ever-expanding universe, stretching its wavelength by roughly a factor of 1,000. As a result, the original brilliant glow has transformed into faint microwave radiation known as the cosmic microwave background, or relic radiation. This is the oldest signal astronomers can observe. We cannot probe any closer to the moment of the universe's birth. Although it may seem strange that this radiation can be studied for decades, in principle even dinosaurs could have observed it, if they had possessed the appropriate instruments. This raises an important question. If the Big Bang was such a brief event, why didn't its radiation simply pass us by? The answer, once again, lies in the finite speed at which signals propagate. Consider a thought experiment. A vast public square filled with people who all shout the same word simultaneously at noon. If the speed of sound were extremely slow, you would continue to hear that shout again and again from increasingly distant people, even though the shout itself occurred only once. The same is true of relic radiation. It was emitted at our location in space billions of years ago and has long since moved on. Yet we continue to receive faint signals from ever more distant regions of the universe. These are the echoes of events occurring beyond our cosmic horizon. Cosmology remains one of the most rapidly developing fields of science, filled with mysteries and astonishing discoveries. We may never fully understand the exact details of the universe's birth. However, the detection of primordial gravitational waves generated during the Big Bang may one day allow us to see the origin of the universe in an entirely new light.